and welcome to CISPA TLDR, the podcast of the CISPA Helmholtz Center for Information Security. In this podcast, we make sense of cybersecurity and AI without all the complicated stuff, so you can make sense of it without a computer science degree. Each month, we sit down with our researchers to talk about the challenges they're working on. I'm Tobias Ebelshäuser from CISPA's communications team, and just so you know, I am not a trained computer scientist either. My guest today is Antoni Kowalczuk, a PhD student here at CISPA. Antoni joined CISPA in early 2024 from Warsaw University of Technology. He's working on making machine learning models more secure. Antoni, great to have you. Welcome to the podcast.
Thank you.
So let's start with you. How did you end up working on AI and machine learning security?
Okay, so I actually started in an ancient times before COVID in 2019. When I started my bachelor's degree at Warsaw University of Technology, I kind of randomly ended up at an event organized by AI Society at my university. Mm-hmm. Like it was kind of a zero to hero bootcamp or something like that, they called it. Mm-hmm. And I wasn't studying computer science back then, but like the whole idea of artificial intelligence and like automation seemed to me pretty interesting from like ever since I remember really. Because like this was kind of the future, right? We are making machines, so we will not have to work. So the more we develop these machines, the more work we can do and the more we progress. So it was always interesting to me. So this was like 6 years ago, I think, right now, which is, damn, it was a long time ago. So this has me started with AI, and I was kind of interested in that for like ever since the attendance to the bootcamp event. And then when it comes to security, it was also pretty random because I wanted to have some more research-oriented bachelor's thesis, and there was like a research group at my university which had different topics for bachelor's students. And initially, I actually wanted to go for a different topic because I was interested in continual learning, which is kind of making machines improve continually with the data. But apparently there was some technicalities with administration and stuff, and the guy that was like the PhD student that was offering this topic redirected me to another PhD student who was then actually working on stuff related to security, data privacy, which eventually landed me here researching that part. So yeah, it was pretty random.
It was a lucky coincidence then.
Yeah, many of those in my life apparently. Yeah.
Great, but now that you're here, recently you have been working on image generation models. I mean, they're everywhere right now. They're all the talk. People use them to turn their vacation selfies into Studio Ghibli art recently. Or, I don't know, even news outlets use them to create illustrations for their latest articles so they don't have to take pictures anymore or pay illustrators. So, but let's start in the beginning. How do these models learn to generate images in the first place, and what's going on under their hood?
Okay, so if you really want to start in the beginning, we have to start with the sole concept of generating stuff. So let's say you want to build a machine learning model. It will be a very not smart example, but let's make the model to generate like the results of throwing a 6-sided dice. So number from 1 to 6. Yeah. So what would happen in the hood, like under the hood, that you want to use this model to approximate the data distribution? And like, what does it mean? So data distribution for like 6-sided dice is like just numbers from 1 to 6 that occur like with an equal proportion of times if you like say throw it 1,000,000 times, right? And if you have a model that actually like approximate this distribution, then when you sample from the model, which means like you ask the model to generate some output, then it should actually like generate, first of all, then generate numbers from 1 to 6, and then generate these numbers roughly in the same proportion. So this is how, in general, the generative models work. And how do they learn is basically they are exposed to like the data distribution. It's so a sample from a data distribution, which for this case would be 1,000,000 of like results of throwing a 6-sided dice. And then like how they generate, you basically have this process of sampling from this approximated data distribution. So this is like the the most high-level idea. And then if you want to go a bit further, then let's say like instead of generating just numbers, so like integer numbers, then you would like to generate images that depicts these numbers. And for that, again, you would collect a data set of number of numbers as images, and you can basically take some fonts from the internet. You can also ask people to draw these images and take pictures of these numbers and take pictures of these images. And then you ask the model, okay, generate me some image of some number. And if the model is trained correctly, it will be able to generate images like containing number 1, 2, 3, etc. And so it will generate images that way. And then if you want to go a bit further, you can also have control over what you want to generate. So let's say I don't just want any number, I want number 1. So then this model has to also recognize from what part of the distribution do you sample, because if you just have distribution of images, like there have different parts of the distribution that corresponds to different numbers. So like let's say number 1 is like in left-right corner, and so then you point the model, hey, I want an image that corresponds to data distribution through this top right corner, which means number 1. And so this is how the conditioned generation works. Yeah,
because the image, so the machine learning model in itself does not inherently know what a 1 or 2 or 3 looks like.
Exactly, it doesn't know anything. It's just a random function, basically.
So just advanced statistics?
Yes, kind of. Yes, this is how it looks like. Then if you want to actually have like images that depict some more interesting patterns than like 1, 2, 3, etc., then you take more data. So you basically, let's say, take 1 billion of different images that are, like, let's say, downloaded from the internet, and then you also have some form of description of what these images depict. Usually it's like the text description. So let's say I have an image of a plane lying on the beach and sunbathing for whatever the reason, but let's say it exists somewhere in the internet, and then it's basically on some website you have this image, and then you have a description. For example, this is used for accessibility things, so for blind people or people who don't see well, for the special software to read it out loud to them. This is how it's usually, like, this is an alternative text. So you have that, and you basically take many images like that with the corresponding descriptions of them, and you once again train the model, which then tries to map out how different text descriptions match with the data distribution that corresponds to these descriptions. And then if you want to generate image, you also ask it, right now in natural text, I want this and that to be like that. And then the model, depending on how good it is, it does what you want to do, or it doesn't, or it does something in the middle.
Okay, but let's say it has a picture of a person sunbathing, and it has a picture of a plane, but it does not have a picture of a plane sunbathing on a beach, because that, I don't know, it might be a little bit out there, but can it still, I mean, obviously sometimes it can, because if any of us have followed social media in the last, few months, there has been a lot of AI slop or brain rot stuff happening, which are pictures that don't make any sense, right? And those are obviously newly generated without the without the AI or the model having seen one of those pictures before. So it is able to actually add different concepts together to build a new image.
Yes, exactly. So back to the example with a model that generates numbers. So let's say you want to generate a mix of 1 and 2. And let's say that these two kind of concepts, as you described in the data distribution, lie next to each other, but the region between them actually doesn't correspond to either 1 or 2. So if you want an image that kind of depicts a combination of number 1 and number 2, then you would basically sample from the space in the distribution that is approximated by this model between those two concepts. So this is kind of high level idea how it works.
Yeah.
But then when we go to models that know many concepts, then these relationships between concepts and like the proximity between these, it becomes intractable. Like it's impossible to like figure out what's where. And then when the actual, let's call like creativity and magic of all this, of the generative models happens, they basically build data distribution that can like entangle many things together without this entanglement or like this mix of these concepts actually appearing in the training data. So they can take things that you like couldn't even comprehend could be done, as you said, like this AI slope that I will maybe refer even later on.
Yeah. Okay. Yeah. Okay.
So this is how it happens.
Yeah. All right. But I think you have worked on a specific type of image generation model. It's called a diffusion model. And can you maybe walk us through how this diffusion model works, how it generates an image from the noise or nothing all the way to a final picture?
Exactly. So like the one crucial thing that I explicitly left out in the description of the generative model in general is how do you actually sample from them? Because they are functions, which means something has to go inside for something to come out of them. And this something usually is, as you said, random noise, which means that to have an image of like, let's say 32 pixels plus 32 pixels, you first start with a set of pixels in like the 32 by 32 pixels that are of random values, which basically they don't correspond to anything meaningful. They don't correspond to each other, and then the model actually learns to transform this random noise to the data distribution. So this is basically transformation from one distribution, which is usually just random Gaussian, to the distribution of the data. And diffusion models work the same, but what they do is they do not perform this transformation in a single prediction step. They basically take the input random noise and then they try to predict into which direction we need to modify this input noise to go to the data distribution. So, and then once this prediction is made, some small step is taken from the initial noise towards the data distribution.
So the data distribution being the final image that you want to see.
Exactly. Yes. And it's trained to do that. So, and so in the first step, it just removes a small amount of noise, and then in the next step, another amount of noise, and you basically do it iteratively, usually like 25 to 100 times or sometimes 1,000 times. It depends on your budget, basically. So you do it multiple times until you actually end up with an image that looks kind of what you wanted to look. So this is how they generate images, and then how they are being trained are basically is the opposite.
Okay.
So given the training image that is like clean image, you sample noise from random distribution, from standard Gaussian distribution. You add this noise to the image, but not all of them, but like some part of it you add to the image. And then you ask the model, okay, given this image where I added some amount of noise, where should we go to get back to this image?
Okay.
So what noise did I add to this image to get this noisy version? And you do it basically for different scales of the noise, so different amounts of noise added. And then during this training, the model actually learns, okay, if I have the noise on the input, then and some direction where to go. So let's say image of a cat as an input. Then what noise, what should I subtract from the input noise to eventually end up with the image of the cat?
So it's like having a final picture, then painting over it, and then just trying to remember what brush strokes I did where, and then removing them the other way around. And by that, you can take, I don't know, if I brush over it and I have just a final image which does show nothing at all, and I just remove one brush stroke after the other until I get to where I started.
Yes, conceptually, yes. That's how it works. Yes, very good.
Yeah. All right. You've talked about training data, so you have to show it a lot of images, right? So as you can said, maybe they're downloaded from the internet, but essentially it says the same. It has to look at a lot of pictures to actually get to a state where it can transform noise into pictures again, right? Can these models memorize the images that they've seen on the internet?
Well, I mean, it has been shown that yes, they do, and they basically can be found. Like the images that have been memorized can be found from these models.
Okay, but then there's a whole lot of problems with that probably. That's why you're here, because you wrote a very interesting paper about that, because you tried to figure out if we can actually look at a model to see what kind of pictures were used in there and if we can tell that there were copyrighted material used in there. So again, let's start in the beginning. What's the actual problem with copyright in image generating AI models?
Well, as you said, like these models have to be trained on some data, because like you have to have a sample of the data distribution that you want to approximate, right? So you have to have some images of cats in order to be able to generate cats. But as you said, some images have, like in general, intellectual property has some laws that protect it, and like allegedly some companies ignored these laws when creating the training data set. What do I mean by ignore these laws? Basically, they went, allegedly, to the internet and just downloaded as many images as it's humanly possible or like useful for the business case. And they ignored, allegedly, the licenses on these images. So they took images that shouldn't be taken and used for training, where it has been explicitly stated in the licenses respective to these images, and they allegedly took these images and trained these models on them. Yeah,
and then images that shouldn't be there because the creator, like let's say a photographer or illustrator, did not give explicit permission for an AI to be trained on it. But if you go on the internet and just download everything, you don't really notice, you don't really care about the license, right? So, because then there's no way to actually tell what kind of license model is for which picture.
Yes, that's one of the problems, is that you don't have an easy association with the training image to the license that it is like covered by.
And it's not only a problem of copyright, it's also a problem of privacy, right? I mean, of course, these images have to be on the internet somewhere in a publicly accessible way for a company to scrape it and train their model on. But still, there might be, there might be you might think differently about it to put it on the internet if you knew that it would be used for training an AI model. Basically, if, as we talked about the person lying on a beach, I might not want to get different pictures generated, trained on me lying on the beach, right? So it's...
Yeah, exactly. And you also couldn't predict that this kind of technology will be out there. Yeah. Like imagine like thinking, let's say when ChatGPT was done, it was in November 2022, let's say.
Yeah.
So like, let's imagine like a person in 2020 putting their like personal images out of the internet on their website, for example, because why not? You can have a blog, apparently. It's legally permissible. And then like asking them in 2020, okay, but are you sure that you want to do that? Because there might be a company that will take that image, download it, and then we'll train a model on it that you will... and this model will be able to generate your face out of your images. And are you okay with that? Yeah. Like, is it feasible? No.
It's always the question of informed consent.
Yes, exactly.
These were like risks that you couldn't even be aware of. I mean, let's not talk about 2020. Maybe let's 2010 when Facebook, came out here in Europe, or nobody was thinking about any of those risks. Yeah. All right. But as you've said, the model could generate my face or my body lying on the beach, but could you give an example of what it looks like when a diffusion model copies or recreates a picture or something it has seen and it shouldn't be able to recreate?
Okay, sure. So there are actually two different types of memorization that are like established in the literature. First of it is like the most obvious, blatant memorization, and by obvious, blatant, I mean the image that the model generates like is almost identical, like in every aspect of the image. So it's not only like the face is similar, but like the wrinkles on the face are in the same places.
So it's just the same picture,
almost the same, like with some small differences, because as I said, you start with random noise, so the process of generation can alter very small details of the image, but it's still like it will be recognizable as like the same image. So this is kind of the verbatim memorization, which is called. And then the second memorization is called template memorization. Let's say you're a company that sells cases for phones, and then they have the same background the same background and the same phone that is used as a model to on top of which
showcase their
their product, and then on top of this model, like seen from the back, they apply different patterns for the cases that they sell. But everything else is fixed. So the background, let's say the background is not obvious, it's just it's also some shapes, something recognizable. But the only thing that is different is the color coding or the pattern on the case. And then the model, because it has seen not only like the one image of this case and the background, but it has seen like, let's say, thousands of these, they can generate the template that has been used by this company, but the cases, patterns might differ and might not actually be the patterns that were anywhere in the training data. So then the substantial part of this image is different from the training data, and we really cannot say that this specific image has been like memorized by this model, but a template of like some part of the training data was memorized.
Because the data distribution is kind of skewed in that direction because it has seen such a huge amount of basically the same picture.
Yes, but like the details, because of the images the images were like initially very very similar to each other, but still different. But because they have been similar, like this distribution was kind of flattened out around like all these images and wasn't focused on the single memorized image, which is the case for verbatim memorization. Like the data distribution in one specific space peaks, and the very specific image is just recreated and memorized in there. Yes.
Okay. So now I want to talk about on how do we get an image. So maybe like for us or for you as researchers, it's very important that you can try out these attacks and see if you can get a picture out, that you can leak sort of sensitive information from the model to actually see if that is a feasible attack and to actually protect the privacy of the users or if the unsuspecting users that the model has been trained on. So, but most of the time we only see the final output from a prompt. So when I go to ChatGPT and say, please generate me an Italian brain rot image, then I only see the final image, but I don't know what the model has been trained on or what is it doing. But your work actually tries to uncover copyrighted material inside a model. How do you even start with something like that, even if it's not applicable to ChatGPT, but we can talk about it later on. But yeah.
Sure. So, I mean, like, let's just jump back a bit to the memorization. So if you can say to the model, okay, generate me an image of a person lying on the beach, and you know what exactly the image of the person on the beach you want to get from this model, and the model actually generates exactly the image that you are looking for, then we can, with very high confidence, almost like 100% confidence, we can state that, okay, this image was in the training set. So like, and you can do that like with any model that you actually have access to. Like if you can successfully make ChatGPT's image generator to output an image from like your personal collection that you put out in the internet, like before the release of the model, then if you can craft the prompt that will output this image, then you can very confidently say that, okay, you trained on my data. But unfortunately, it's extremely hard to like get this kind of confirmation that there was illegitimate usage of the training data. But there, for one very big model called Stable Diffusion, which was from like 2023, there is a research paper that basically took this model because it's open source, and they generated 175 million of images from like many different prompts. And because the training set of this model is disclosed, they was successfully able to identify like 50 images or like 550 or 500, I'm not sure, images that has been memorized by this model verbatim. So you can do that. But as I said, it's extremely costly, and like any provider will just rate limit you if you tried that. So like, good luck. So it's not possible that way. What is a different approach is something called like membership inference attacks. So basically here you want to actually ask the same question, like, okay, I have this training image, and was it trained or like was this model trained on this image or not? And this is way more complex problem, because like you not simply just ask the model, hey, generate me that specific image, and you get some output. But you also have to have a set of images that you know that were not for sure used to train the model. And then you see, okay, how does the model behave given like my suspect sample, my suspect image? And does this behavior differ for my image versus the images that I'm sure was not used to train the model? And if you can do that confidently, like if you perform a successful membership inference attack, then you can, like with some confidence, state, okay, this model was like with confidence of 99% trained on this very specific image. So you can, theoretically, you can do that.
Yeah, but there's probably some caveat, because you have to be able to actually look at the steps the model performs, right?
Oh, yeah, like not necessarily steps, but you have to have more insight into the model. So usually you would have to have more access than just like API model, like API to the model, which just returns the image. So like if we can go back to like the basics of membership inference attacks, so let's have the model that outputs how much is the probability that the person has lung cancer given it's just X-ray. So you would have the access to the model that will output these probabilities, which is usually not very common. Usually you should just have yes or no. And then you would also have to have, like, let's say, thousands of images that you know were used to train the model, and you then another 1,000 that you know that were not used to train the model. And then you will design some kind of behavior metric from this model. And then given those 1,000 members, by member, I mean a sample that was used to train the model. So you have 1,000 members and 1,000 non-members, so the samples that wasn't used to train the model. Then for each sample in the member set and non-member set, you collect some form of behavior metric, and then you compare these behavior metrics between these members and non-member samples. Yeah, and only then you can assess how strong your method is really, and how actually good you are in this attack. So, as I said, like you have to have way more access first and foremost. Second, you have to actually know part of the training data, and you have to know part of the non-training data in order to execute that. And also you have some strong assumptions between those training and non-training data, because if the difference in behavior that you observe after like running your membership inference attack stems from something else than the fact that the model has been trained on members and not on non-members, then you will never be sure that this difference actually is due to this training.
So going back to the X-rays, it could just be that, I don't know, there's some text somewhere on the on the X-ray that
or
is
just
not
the date is different.
basically. It is not in the other parts of the training data set.
Exactly. So like you have this assumption that members and non-members are independently and identically distributed, which means that there's no way of distinguishing members from non-members. But when you apply like this kind of measurement based on the model, then some differences will actually pop out. Yeah. So these are strong assumptions, unfortunately. And so this kind of attack is not really applicable to like models closed behind API. But still, this is like an active area of research for like a bit, maybe a bit different view on data privacy.
Yeah.
So like the core idea after like behind the membership inference attack was, okay, let's say I'm not really ethically correct insurance company. And I want to know if the person that applies to me to like cover my health expenses, does it have lung cancer or not? Because that will be very important for me as an insurance company to have that info, because then I can jack up the premiums up to 100x because that like there will be expenses. But this kind of thing actually is a private information that this company shouldn't have. But let's say the company has access to a model that actually was trained on people with lung cancer, and then this model wants to predict, okay, how much time does this person have until it dies or whatever. Like
and these models do exist, right?
Yes. So. These models do exist, and like from the perspective of developers of such models, it's super like good for society and everyone to like have these models trained the best as possible and then release it so others can use it, right? Because like you're making a favor to everyone if you do that. But unfortunately, then if you have the chest x-ray of a person and you're not a doctor, you're just like insurance company analyst, and you have access to this model and you successfully state, okay, this person actually was like this image of like chest x-ray of this person was used to train this model that predicts something about lung cancer. So if you can state that, then you can actually learn some new information about this person. Okay, this person has lung cancer. Premiums go 10x.
Yeah, that is something that shouldn't be possible, right? Because this private information used for the, as you said, good of society, but it can also be harmful if it gets in the wrong hands, which is why you work on privacy.
Yes, exactly. I mean, attacking is more fun than defending, but but still, yes.
But still, as you said, it's an active research area, and we will get back to what it can be used for right now. But your work in your new paper goes a bit further, because you're not using membership inference, you're using something else. Maybe you can tell us a little bit about your paper and what your new approach is.
Okay, sure. So, I mean, the approach isn't really new. It's called dataset inference, and it has been used before for different models than even generative ones. So one major limitation of membership inference attacks is that with the increase of the model size and the training data, and like with increase of basically everything, the efficacy of membership inference attacks goes to random guessing, basically.
Okay.
So like this kind of attacks become almost useless, and with this increasing scale of the models, it will just not be useful in any case. Yeah. So dataset inference works a bit differently. So first observation that dataset inference is based on is that signal from this behavior differences between samples in general, like single images in general, is very noisy, which means it can differ just based on how the image looks like. So let's say like generating cats is easier than generating dogs. And then you have an image of a dog and an image of a cat, and the image of the dog was actually used to train the model, but the model behaves worse on this image, whereas it behaves better on the image of the cat, which wasn't in the training data. Yeah. So you have this kind of problems with single samples. However, like if your behavior metric that I mentioned is well created and like well defined, then you will always observe some difference, but not on the level of singular samples, or so images in that case, but on the level of sets of images. So like, let's say you use model error as your behavior metric. And model error is basically what any like machine learning models aim to minimize to behave well on some task. So here, like for the diffusion models, this error would be how far off you are with your prediction of, like, as you said, the brush that was added to the image from the actual brush. And like, the smaller this discrepancy is, the better is the model. And like the sole assumption behind like both membership inference attacks and the dataset inference is that like the model error will be smaller for members, so like the training samples, than for non-members. Always. Like it will be always smaller, but like not on the level of singular samples, but on the level of like set of samples. So on average, it will be smaller. And so now you can think about it as a set membership inference attack, kind of. So you ask the question, is the set of samples used to train the model or not? And you compare between two sets of samples, not two singular samples. And basically for each sample, you will have some behavioral metrics, but then you will compare how these metrics are distributed for both of the sets. And if there is a significant difference between like the averages, or like this distribution of this behavior between those two sets, then we can say, okay, these sets, like without the context of the model, are identical. We have no way of distinguishing them from each other. But when we collect behavior metrics for like our suspect set and our non-member set, then there some difference actually appears out of nowhere. And this nowhere, like the only way it can be different is that if the model was actually trained on the suspect set. So this is how it actually builds up.
Okay. So the word behavior metric kind of sounds a little complicated, which I think, of course, it is. It's always complicated once you go into the nitty gritty, but it basically means that you look at what the model does and how it behaves, right?
Exactly. Yes.
So metric just basically means that you have to have some way of measuring what it does, right?
Yes, exactly. Like you have to basically, like, by behavior metric, I mean a number. So like number bigger for members means that for non-members on average means, okay, like the model was actually trained on members.
And it might make sense to actually look at, like, as you said, data sets, because I don't know, if I'm a photographer and I don't want people to train their models on my images, it's very unlikely that I only have a single image on my website, right? Because I don't know, if I'm a landscape photographer, there's not only one landscape, there are different pictures and the different styles, and then you can bundle them all together to, I don't know, be sure, or no, sure is a word we don't really use, but to have higher confidence. That
exactly. That's the way. So the nice thing about it is that if you collect more samples, then you will eventually like limit your uncertainty. Because like we use statistical testing, and like basically the thing that improves the power of the statistical testing, which means how sure can we be with our like observations, like it increases sometimes, like, I don't know, almost exponentially with the amount of data points in the sets. So yes, so this is one of the use cases. So let's say like you can be a photographer with like 1,000 images out there. You can be an artist with like 100 of images. You can be very big stock photos company, which has like tens of thousands of or millions of images out there. And then you can basically see, okay, but like if we just treated every image separately instead of grouping them together, we wouldn't have like achieved anything. But when we group them, we can have very, very strong method.
Okay, but let's say on my website there are 100 pictures, but the model was only trained on 80 because the 20 latest ones were like at the cutoff point when the model scraped all the data. What if I then compare it to this 100 pictures? Will it basically poison my data set group, or is it robust enough that it doesn't really make a difference?
I mean, yes, it's robust. That's the cool part. So, like, we tested it out actually, and for some models, if you have enough data, so let's say if you have 100% of clean images, so like your suspect set is 100% images that were used to train the model, then if for this model we need only 1,000 images to like for our method to work, then if we extend it to like 10,000, but only like 1,000 of these images were actually trained used to train the model, then the method will actually still work.
Okay.
Yes.
Which is a significant amount. So,
yeah. I mean, we did many experiments like that.
Great.
So it was cool. Yeah, like in the paper, the lines are like very satisfying because like with the amount of let's say poisoning, like if it increases, you just need more data and it will work.
Okay, that sounds very promising, and it also sounds very powerful. But as you already explained, it is tough to, or basically not possible to use it for existing models that you as a user don't have really have access to, basically. So with ChatGPT, as I said, you put in a prompt, you get out an image. You don't get to measure any behavior metrics, but so as I've understood it, your method won't really work with a lot of commercially available models. But still, where do you put that research? Will it still help us towards gaining a better understanding?
Well, just to clarify, it will not work on any commercial model.
Okay.
So just to be clear.
Yeah.
Yes, but like the question is very, very correct. Like you have to ask, why on earth do we even care? And one of the thing in like the privacy research is that like it started relatively. I mean, for machine learning models, it started recently actually, and like the methods from the very beginning were very, very prototypey. So like you have a massive amount of assumptions that you have to meet in order to achieve anything.
Yeah.
And then like there have been breakthroughs over breakthroughs over breakthroughs, and eventually like you arrived at very strong methods, but still like you have many assumptions still left to address. And every method also has its limitations. So like overcoming these limitations is also important. So our method overcomes limitations of membership inference attacks, which like up to like, let's say 2023, I think, were like the gold standard in like the privacy research to like analyze how risky, like how much privacy is leaked through the models. Yeah. And by privacy leaked, I mean the example with like the insurance company and the like cancer predictor model.
Basically someone gaining information, private information from a model that they should not be able to.
Exactly. Yeah. So like the membership inference attacks were like the gold standard back then. And I think there is still kind of our gold standard because many of like the machinery around privacy research was actually like centered around single sample stuff. So like the core idea of something called differential privacy, which is like the framework that will provide mathematical guarantees that you cannot execute membership inference attacks successfully like against any sample possible. So like this kind of framework was also built on like single sample intervention.
So basically building a defense against those kind of attacks.
Exactly.
So nobody can.
Yes, but this was before actually membership inference attacks were named.
Okay.
So like this is work from like 2006.
All right.
Yeah. So like the whole focus was around like single sample interventions, but like nobody really cared about like, okay, what if we scaled it up to a set? I mean, maybe nobody cared is not correct, but like it wasn't the main focus of it.
Yeah.
But once we show that, okay, like if we can go beyond a single sample, we can create more powerful attacks because our method like can be seen in two ways. First of all, it's like, okay, I have an artist that has like painted 100 images and then put it out in the internet, and they have been quote unquote stolen from here to train the model. And so this is one use case. But second use case is also, okay, I have a set of 100 people with their chest X-rays, and I have the model, and I can test, okay, Like if in this set of people, are there people with lung cancer or not?
Yeah.
So like, and this attack is like very, very much more powerful than the previous one.
Yeah.
Like in the execution, because like even with the growth of the model or like growth of the training data, it still works. And it still will work because it's kind of like it's almost guaranteed for it to work, because there always will be some gap between like the model error on the training data and on non-training data. So it's just how these models work. So we provide way more powerful attack, actually.
Yeah.
And this kind of attack can also be then explored and see, okay, how can we defend against that? Or how our models are vulnerable to this kind of attack. So we can use it both ways. So one for copyright resolution, but then for red teaming.
Yeah. And red teaming maybe can...
red teaming, sorry.
It's a fun word that always pops up. But.
Yeah, red teaming is cool. So red teaming basically says, okay, we let's say you are a company that trains some model, and then they want to actually release this model in a wild, like the population, and see what happens. But they also don't want to get sued. Usually. Sometimes they just don't care. But let's say they don't want to get sued. So they first have to test, okay, like given this model, how prone it is to different attacks. So for large language models, it could be jailbreaks. So like if I am OpenAI, I probably don't want my model to explicitly say, okay, if you want to create a nerve gas, this is what you do. So this is jailbreak. So you have to defend against that. And if you are like image generative company, let's say like Midjourney, then you probably would not want random people to actually learn about your training data set. Like it doesn't matter if you stolen images from the internet or you have everything like in permission, you just don't want other people to know your training data, right? And red teaming will actually test how much risk is it in the model. So they will, like during red teaming, you will attack the model from very different angles. So you will use membership inference attacks, maybe our method to validate how are we standing on this privacy risk.
Yeah.
So this is where it can be used for.
Okay. So your method basically helps us make those machine learning models that are very promising to better our lives, as in the medical sector, identifying cancer, identifying diseases, to actually make sure they don't do, like, let's say, unintended harm, right? Because with every new technology that uses our private data, there's always harm that we might not even think of. Because, it's always, I mean, of course, it's often also an afterthought if you're a commercial business that wants to make money as fast as possible, right? So what I think is interesting is, as you said, like Midjourney, they don't want people to know what their data set looks like. Do you think that is good? Do you think that AI companies should be required to disclose their training data, or is it something that doesn't really make sense?
Well, first and foremost, I would like the companies to obey the law. That's like it's wishful thinking, obviously. This is a tricky question, because over and over again, it has been shown that like a lot, and like I cannot emphasize how much of the model performance and like how potent it is, how effective it is at the task that it executes, stems from the quality and the amount of the training data. Like imagine like this is the gasoline for the car. Like let's say you have a Ferrari or something, but then nowhere on the earth you can find gasoline and or any produce to create it. You have a fancy piece of trash that looks cool, but like cannot do anything. So basically data is the gasoline for these fancy models. And because it's so important, this is often like what distinguishes different companies and their products between each other, the training data that they use. So like I'm fairly sure that like 80 to 50% of the people that work on OpenAI actually work on making the data as high quality as possible, as diverse, as abundant, as informative, as it's humanly feasible to train their models. So because so much work has to go into that, I'm not sure if it's like economically feasible to actually force these companies to disclose this, because part of their competitive edge actually, like significant part of it comes from their training data like acquisition processes.
Which also incentivizes them to just don't care about copyrighted material. I think actually Sam Altman, the OpenAI CEO, actually he just blatantly stated that if AI companies have to obey classical copyright laws, they just lose their business case. So
yes, I mean, and I fully agree with what he says, unfortunately.
Yeah.
Yes, so this is like, I mean, this is, you have this trade-offs, right? Because, I mean, personally, I'm a heavy AI user, like AI assistants from ChatGPT to like AI coding assistants. Maybe not so much like agentic AIs, but I'm looking forward to it because I've been trying out it and it's amazing.
Okay, what exactly do you mean like
agentic AI? So like the model that just like, okay, I want you to create me an app that has XYZ.
Okay.
And like you like type it and like you wait like an hour or so and you end up with a finished app. It boosts my performance and my productivity like by half probably. Yeah. So like I'm heavy enthusiast of that technology. I think it's awesome and it will get better.
Yeah.
And I want it to be better because it helps me so much, and it helps not only me but like many people, and it creates like insane value. It's like for me, I feel like it's like Microsoft Excel, which transformed the economy and like how people make business 20 something years ago. Like world is way different after Microsoft Excel, and seems to be different after ChatGPT.
Yeah,
so
that's true.
Because I think that there's such a massive value in that, I'm kind of puzzled because like I understand that privacy is very important, and that's why I kind of do research in that because otherwise we'll be just wasting my life here. And I understand the concerns, and I want companies to be more accountable, like when it comes to how they use private data. But we also have to figure out a solution that will not just straight out kill business cases for these companies.
So we have to basically thread the needle of respecting also like copyright laws and like an artist also has a right to know how their work is being used. So it seems like there's some work to be done also by lawmakers and society as a whole, right?
Yes, exactly. It's a very open case. Like this technology, like before ChatGPT, nobody believed that machine learning can work. Yeah, and apparently, we are discussing ChatGPT.
Yeah, I mean it's everywhere, right? Yeah. I don't know if you could talk to a single person on the street who hasn't heard of that in the last few years. So
I mean, this is everywhere. Like the fastest growing product in the world. Yeah.
It also means that there's a lot of work for you to do in the next few years. Sounds like you're not out of a job.
Yeah, I have job security.
Do you already have an idea of what's the next big challenge you're tackling?
I don't think if it's a big challenge, but I can talk about what I do right now.
Yeah, sure.
Right now, I'm basically working on this memorization problem in diffusion models that I described previously, because people work on memorization ever since it has been shown that, hey, it happens. And also people want to have methods to like remove this memorization from the model, because like if the model is able to generate very specific training sample, it means it's something in the weights of the model, right? Yeah. So given that you know that it's somewhere, then you maybe want to look out where it is and try to edit it out. So the model no longer outputs that. And there are a couple of methods to do that. And our research basically says, okay, that these methods don't work. And we want to create something that fully deletes this memorized images.
So it basically goes into the direction that even the developers of an AI model don't really fully know what's happening under the hood in every case.
Nobody does.
Yeah.
Nobody knows what happens under the hood. Really. like really, this is one of the problem. Like explainable AI is a subfield which is enormous right now.
Yeah.
So and still nobody knows really. Like we have some assumptions, we have some ideas, we have some insights. We can do some stuff like with the model. Like we can do very, very precise editing of things. We can, for example, right now it has been shown that it doesn't work, but like there have been a lot of methods that basically say, okay, my model can generate harmful stuff, like or not necessarily harmful, but harmful in some contexts, like nudity. Yeah, harmful for children, right? Yeah, maybe not for adults. Yeah. If you want to see that, but
still, if you generate a nude model of a person that does not want to.
Yes. Like if you put a face on it, yes, obviously. But like, so like you have this kind of concept that it's nudity, and you want to like erase it. Yeah. So like you don't want to train the model from scratch without any concept of like nudity. You would like to make some very simple intervention, like edit some parameters of the model, some weights, and basically then say, okay, we did this super simple, because these methods are actually simple. Yeah. Super simple intervention. Everyone can do that. We have a code. And we basically can obtain a model that is as performant as before, but just is not able to generate nudity.
And then you can just jailbreak it and
then... but like these methods were believed to actually work. Okay. But like there have been some new papers that actually broke it. So like it's back and forth.
Cat and mouse game.
Yes, exactly. Yeah. So like the same happens actually with just memorization mitigation. So we know a lot. We can pinpoint some behaviors like that are actually distinct for memorized images, like how the model behaves. So like this behavior metrics, basically, we can have not only for like assessing membership of the samples, but we can also use them to assess many different things. Like, is the image like safe or not safe? Is it memorized or not memorized? Like you can collect many different numbers, and then based on these numbers, you can say, okay, we probably know why model shows this kind of metrics given this image. Okay. So like there's sort of work that actually kind of works, but like we show that not really.
Okay, that sounds fun. Maybe then you'll join us again for an update.
Very soon. Looking forward to that.
Yeah, but before I let you go. It's always time for our famous quick questions in the end. So, question 1: what is the most surprising thing you have learned on your cybersecurity research so far?
That it's actually not that scary and not that like alien and like this is not as dark forest as I thought it was.
So you're not all wearing hoodies and working in dark basements.
I mean, I cannot speak to that, but no, I meant like complexity and amount of like insight and like how good you actually have to be to do that. Or I'm just like have an imposter syndrome or whatever. But still, it's just maths and not very complex one, and concepts interacting with each other. And I think it's like if you dig deep enough and you have will to dig, then it's straightforward.
Okay, sounds like you're recruiting.
Well,
so second question: if you could instantly solve one cybersecurity problem, what would it be?
I would like all the scammers to disappear.
I think that is more of a societal problem then. Yeah.
Well, I mean, it translates to cybersecurity.
Yeah, definitely. I'll it counts, definitely.
Nice.
So, what is more intimidating to you? A machine learning model that's not behaving right, or a paper deadline? You as a PhD student?
I think neither is intimidating. Like I can just shout at an LLM to make it do the job most of the time. And for the papers, like there is always another deadline.
Yeah.
So
it's nothing to be afraid of.
Yeah, like it depends on how well do you handle pressure from your supervisors.
Yeah, okay. I think that makes sense. Yeah. Question number 4. What kind of rules or technologies do you hope to see in the next few years to make generative AI more fair and transparent?
Yeah, well, I will. Then now is the time to go back to AI slope that you mentioned.
Yeah.
So, like, it's actually very interesting phenomenon that you mentioned, like with obviously AI generated images that don't depict anything real. Let's like say there has been something very popular, like the AI generated image of Jesus made out of broccoli or whatever. And then the fan page was like, had like 50,000 reactions and like people were saying God bless and stuff in the comments. And then you will see like this fan pages, like the sites on Facebook to like pop up like tens of thousands of them, like just randomly.
Yeah.
And then after they reach a certain following, they kind of switch the narrative to be literal Russian propaganda.
Okay.
So given that, I would really, really like for it to be a mechanism that can identify this kind of images.
Yeah.
Because there is nothing working like that.
Yeah.
So yeah, that would be cool to like have something that reliably can say, okay, this is AI generated.
Yeah.
Because we don't have that.
Okay. Yeah, that's true. I mean, it's a whole field of research also at CISPA, and it's not getting easier.
Yes, exactly. And you can go beyond images. You have to go to the text.
Yeah.
The text
Voice.
level is super.
Yeah.
Voice, like you have hundreds of like scams with like AI generated fake deep fakes that are like, I've heard about companies losing millions of dollars because somebody was like basically pretending to be the CEO and say, okay, I'm the CEO. Let's go for the Zoom call with me. And you have to now transfer $50 billion.
It's the CEO scam just on steroids, basically.
Yes, and like these images and these videos, like in real time, are almost indistinguishable. Yeah, and there will be more because like the models, like the quality of video generation in recent years came from just uncanny valley to holy crap.
I think there was like a video of Will Smith, the actor, eating spaghetti, which was like it was a very famous example for what it could look like. And I think like only last week I saw a video where I don't know, if I didn't know it, I would say, quality is a little off, but
but it's like 1 year of progress or like 2 years of progress. Like imagine what will happen in like next 2 years.
Absolutely crazy. Yeah. Right. Scary, but CISPA's working on it. There's a lot of people working on it.
We'll solve it, guys, for sure.
We don't. More money. We have to offer some solutions, but I don't know. It's definitely a challenge, but I'm glad that you and all your colleagues are working on it. So there is one last question for you. If AI could take over one part of your work as a researcher, what would you happily hand off? I think you already talked about that you like to use some. But like this is kind of a support. Yeah. What I would like them take off of me would be dealing with people, because I'm absolutely horrible with that. Okay.
Yeah, and I'm also deeply aware that like dealing with people is the skill that will push me and push everyone very, very far forward, because like you build stuff in teams. Yeah. Yeah, but I'm total crap at that. So yeah, if I can like take over, like clone me and like have a version of me like way better than me to like interact with people, deal with people, then then I will
ChatGPT, please socialize for me.
Yeah, exactly. Please network for me. Then, like the possibilities that I could get would be insane. Yeah, I will probably quickly be somewhere else.
Yeah, I think it's all just you have to put in the work and then you'll get better. That's nothing that AI will handle for you. I think you'll be fine.
I wish there would be technology that would just in real life help me. Okay, now smile. Now to keep eye contact. Now I don't know, say a stupid joke. Okay, awesome. You don't know what joke you say. Okay, I will generate something for you. Don't worry, based on the social cues that someone else can do. Yeah.
Yeah. So if you're out there listening, this might be an idea for your next big business project.
Yeah, I will buy it for sure. Like, get my money.
All right, Antoni. Thank you very much. I've had a lot of fun learning about image generation models and how to attack them and then ultimately also make them more secure. Thank you very much. And I wish you all the best for your future work, and maybe we'll have you here on the podcast again.
Yeah, looking forward to it. And thanks for having me. It was fun.
Thanks. And that's it for this episode of CISPA TLDR. So if you want to learn more about his work, check out the links in the show notes. And if you enjoyed this episode, make sure to follow or subscribe wherever you get your podcasts, and leave us a rating if you're feeling generous. It really helps others to find the show. So I'm Tobias Ebelshäuser. Thank you very much for listening, and see you next time when we'll dive into the next big topic in cybersecurity and AI without all the complicated stuff.